A square of sky smaller than your palm holds the most patient experiment ever performed. We pointed a spacecraft at that one patch, and for years it stared, unblinking. No motion, no color change, no fireworks. Just a steady pulse of light that occasionally flinched. From those flinches, we found other worlds. It is a strange truth that a shadow, not a picture, tells us more about reality. The faintest dip in starlight can outweigh all the brilliance we see. Imagine the paradox. The smallest sign reveals the largest thing. A planet, invisible and cold, leaves its fingerprint by making a star dim for a heartbeat. What kind of logic is this? Where loss creates knowledge. We call it the transit method. But really, it is astronomy's whisper test. A 1% dip means a world as big as ours, orbiting a sun light years away. If precision can conjure continents, how far can patience take us? Picture the device. Kepler's metal eye fixed on Cygnus, thousands of stars shimmering on its detector. The telescope does not blink, it only counts. Each photon lands where it should, until suddenly fewer arrive. The data drops, the line dips, and we know something has passed between us and them. At its core, this is geometry written in light. We measure time, depth, and frequency, and from those numbers build the unseen. To see how delicate this is, hold your hand in front of a lamp. The glow still fills the room, but a fraction fades. That fraction can tell an observer your position, your motion, even the shape of your fingers. Far away, a world crosses its sun and tells us its size. We have never photographed it, but we can name its orbit. How many shadows must we trust before one becomes a place? Now lift your eyes from that single patch to the Milky Way's great curve. It looks calm, yet its calm is deceit. A ribbon of stars arcs across the night, but threaded through it is a faint stream, the remains of a smaller galaxy, pulled apart and folded into ours. The Sagittarius stream flows like a ghost river through the disk, its stars older, slower, slightly out of tune. From their motions, we learn that our galaxy once fed upon another. Creation here is not gentle, it is hungry. The question deepens. If galaxies eat their kin, where did the ingredients for our sun come from? Some astronomers suggest that as Sagittarius broke apart, it released cold hydrogen that rained into our young Milky Way, kindling a burst of new star formation. Our own star might be one spark from that meal. Think of a dry field suddenly drenched by a hidden flood, seeds waking to life. Could our existence trace back to that moment of cosmic collision? In the same sky where planets dim stars, rivers of stars reveal cannibal histories. The clues are faint, yet they fit. A planet hides in a single shadow. A galaxy's crime hides in a thread of misplaced motion. And at the very center of it all lies another puzzle, darker still. Near the galactic core, stars whirl around nothing. They race as if pursued, but their pursuer is invisible. Their orbits sketch an unseen mass so compact that even light cannot escape. Time itself falters there. We call it Sagittarius A, the black hole at our heart. No camera can frame it directly. Only the paths of stars betray its pull. What else could move a million suns with silence alone? Stand at the edge of a waterfall and feel the rush tugging forward. That is how these stars live, balanced between orbit and fall. If they drift a little closer, they stretch like threads, torn by the gradient of gravity. We imagine falling, body first, then time itself unraveling. Spaghettification sounds absurd, yet the equations allow nothing else. The edge of knowledge has a shape, and it bends inward. Beyond that abyss lies a glow so ancient it pervades everything, a soft microwave haze left from the universe's first light. To the naked eye, it is darkness, but to our instruments, it is pattern, a faint stipple of temperature written across the whole sky. That texture, the cosmic background, is the afterimage of creation. It hums beneath every signal we measure, the oldest photograph in existence. Between the infant glow and the silent center stretches the story we are built to chase. Small effects, immense meaning, a planet's dimming, a galaxy's meal, a black hole's clock. A whisper from the first second, all of them hints that precision, not spectacle, is the key to truth. What does that imply about us? The creatures who notice. Why do we trust numbers more than light? Shadows more than pictures? Our tools are humble but exact. Photometers that do not blink. Antennas that taste radiation older than stars. Probes that skim a star's atmosphere and survive the wind. They all serve the same creed: stay still. Watch long enough, and patterns will confess. Every discovery begins with refusing to turn away. Hold that thought. The cosmos rewards endurance, not haste. It hides answers in margins, in ripples, in faint lines of motion. We will follow those margins into the chapters ahead, tracing how shadow becomes map, how hunger becomes creation, and how the end of light becomes memory. If this journey into measured light speaks to you, like and subscribe to the Quiet Universe channel. The clue begins with a single flicker, a dip in brightness no wider than a breath, repeating with the calm rhythm of a clock. To most eyes, it would be nothing, a numerical hiccup, a flaw in the sensor, but to a trained one, it is an orbit made visible. Light should be constant, yet here it trembles. That tremble is a planet's shadow sweeping across its parent star. The star does not move. The planet does not shine. Yet together they write a pattern of light that speaks of size, distance, and time. The telescope that first caught such whispers, Kepler, was less a camera than a metronome. It fixed its gaze on a single constellation and refused to blink for years. Every photon counted. Every pulse logged. Nothing spectacular. Nothing cinematic. Just brightness against time. The patience was monastic. While the world below spun through seasons, Kepler watched the same stars fade and recover. Fade and recover. A symphony of minor notes written across 1 billion miles. Why does this method work? Because even stars obey the simple logic of geometry. When an orbiting world crosses in front, it steals a portion of the starlight. The depth of the dip tells the planet's size. The interval between dips marks its year. The curve's shape reveals how cleanly it crosses, hinting at tilt, clouds, or rings. From a signal smaller than a heartbeat, entire worlds are reconstructed. A stranger's orbit, an atmosphere, perhaps even weather, all carved from silence and light. Think of a pulse on a medical monitor. The body behind it is unseen, yet the rhythm betrays its condition. In the same way, each star's flicker tells us if its companion is healthy, erratic, or hiding more secrets. Sometimes a second dip appears, the planet sliding behind the star. That tiny extra darkening measures how much light the planet reflects. So, in principle, we glimpse its albedo, its temperature, its ability to bear day and night. For a species limited to one solar system, such reach is staggering. But truth never comes alone. Every clue breeds a contradiction. Not all dips mean planets. Some come from binary stars, some from sunspots, some from dust drifting across the line of sight. Astronomers must filter the false shadows from the true. They compare multiple wavelengths, seeking the fingerprint that matches an orbit rather than a blemish. Even a single misread can invent a world that never was. How do we trust our eyes when the cosmos itself is a master of repetition and disguise? At its core, the transit method depends on trust in pattern over picture. It demands we believe in math before sight. To put it another way, the data teaches us humility. A world does not announce itself in color or motion. It appears in subtraction. The telescope does not show us a new landscape. It removes one photon in 100 and dares us to interpret the loss. We are reminded that knowledge often begins as absence. On the ground, the lesson is easy to reproduce. Hold a candle steady, pass your hand before it, and measure the dimming on a simple sensor. The number drops. Repeat, and a rhythm forms. You have mimicked a transit. You have become, in miniature, an observer of worlds. The simplicity hides the enormity. This is the same principle by which thousands of exoplanets have been found. The same humbling method that made us realize we are not unique. Every confirmed world adds a point to a growing map, a constellation of possibilities. Some orbit twin stars, locked in graceful resonance. Some skim so close to their suns that metals boil in their skies. Others drift in habitable zones where liquid water could rest, the quiet middle ground between fire and frost. Each orbit defines a different kind of time, a rhythm foreign to ours yet bound by the same gravity. The diversity should be chaos, yet patterns emerge, families of systems, echoing in harmony. And from these patterns comes something human. We name them, not for ownership, but for belonging. Kepler 22b. Japest 96b, cold labels that mask the wonder beneath. They are not mere coordinates. They are the growing vocabulary of our reach. When the first Earth-sized planet was confirmed in a habitable zone, the announcement was not shouted but whispered in equations. A dip, a curve, a match. That was all. Yet it meant everything. Why does this matter? Because it changed the frame of loneliness. Before the transit era, planets were theories, rare jewels orbiting distant suns. Now they are routine, as numerous as grains in a beam of light. The night sky has turned from decoration into population. Somewhere in that abundance, the same physics that made us may have repeated itself. The idea does not inflate the ego. It dissolves it. We are no longer the center. We are one of countless results. Still, the question lingers. If we can weigh a world by its shadow, can we ever know its face? Direct imaging remains rare, blurred, a trick of coronagraphs and software. Most of our discoveries remain silhouettes. Yet even in that limitation lies meaning. Shadows force us to imagine the source. They remind us that knowledge is never complete, only approximated. Each new transit refines our estimate, narrowing the space between guess and truth. This is the paradox of modern astronomy. To study the brightest things, we must measure the faintest absences. It is not heroism, but discipline. The instruments are quiet, the discoveries incremental, yet the result is a revolution in worldview. We have gone from wondering if other worlds exist to cataloging them by the thousands. The grain of sky, once thought empty, now teems with orbits, each one a silent clock circling its sun. So we look again at that original patch of Cygnus, a mosaic of light no wider than a coin held at arm's length. Within it hide hundreds of confirmed planets, and likely thousands more waiting. The pattern is endless. Every flicker, every repeat, every faint echo of dimming says the same thing: the universe builds worlds as easily as sand builds dunes. We have learned to read those dunes in light. We have learned that absence is information. And yet, even as our list grows, a deeper mystery rises. These worlds exist, but how did the stage that holds them form? What fed the stars that spawned their suns? And why at that moment, the next step lies not in shadow, but in the motion of entire streams of stars, torn from their homes, carrying the ingredients of creation itself. Across the quiet arc of the Milky Way, a slender thread of stars drifts like smoke, faint yet deliberate. It is the Sagittarius stream, the remnant of a smaller galaxy being pulled apart by our own. Each star within it is a refugee, torn from its home and folded into the body of the Milky Way. To most eyes, it looks like nothing more than a faint smudge. But to those who track the motions of thousands of suns, it is a confession our galaxy has been eating its neighbors. The clue is motion. Stars born together share a direction. a rhythm of orbit that marks them as kin. Yet here, woven through the disk, is a current of stars whose paths do not match the rest. They swing too high, dive too low, and loop around the galaxy in a stream that crosses the familiar plane. Like a ribbon caught in a whirlpool, their alignment makes no sense unless they come from outside. The Milky Way, vast as it is, does not grow by itself. It consumes, and each meal leaves behind this kind of trace. The contradiction is elegant. Galaxies are often pictured as stable, rotating pinwheels, serene and symmetrical, but the Sagittarius stream shatters that idea. It proves that even our calm home is a cannibal, reshaped by past collisions. The edges of the Milky Way are not boundaries. They are scars. Every orbiting satellite, every dwarf galaxy drawn too near, is stretched until it becomes a filament of stars. The process takes billions of years, slow enough to look peaceful, yet the result is chaos arranged by gravity. Why does this matter to us? Because those collisions may have created the conditions that allowed the Sun to form. When Sagittarius first fell into our galaxy, its gas and dust mixed with ours, compressing clouds and shocking them into new bursts of star formation. Astronomers studying metallicity, the fingerprint of chemical richness, find that the Sun's own composition carries a hint of this timing. It was born around the same era the Milky Way was most active in its cosmic feasting. Could our star, and by extension, our existence, be the aftertaste of a collision? Imagine two rivers meeting at an angle, one swift and cold, the other wide and slow. Where they join, the turbulence churns the sediment, lifting nutrients and oxygen from the bottom. Fish gather there. Life multiplies. The galactic equivalent of that confluence was the merging of Sagittarius and the Milky Way. The stream did not merely add stars. It stirred the galactic medium, pulling fresh hydrogen into regions where it could collapse into new suns. Our solar system may be the child of that mixing zone, formed in the turbulence of union. At its core, this is a story about recycling on the largest scale imaginable. A galaxy eats another, yet nothing truly disappears. The stars keep orbiting, the gas becomes fuel, and the metals forged in old suns seed the next generation. To put it another way, the Milky Way is a compost heap for starlight. Every decay feeds new birth. The Sagittarius stream is proof of this endless metabolism, visible across the sky as a looping bridge of stars connecting past to present. The evidence does not come from pictures but from motion. Satellites like Gaia measure each star's position and drift with such precision that patterns emerge from apparent randomness. When plotted, these stellar velocities draw a luminous river winding through space. Some portions move toward us, others away, like alternating tides in a cosmic estuary. In that pattern is the ghost of a galaxy long dissolved, its bones now part of ours. Still, questions haunt the map. How many such streams exist, faint and unrecognized? How many times has the Milky Way repeated this act of quiet violence? Some researchers estimate dozens, maybe hundreds, of swallowed companions over billions of years. Our galactic halo, once thought to be a formless cloud, may in fact be layered with these threads. The sky above us is a palimpsest, each new layer of stars written over the faint handwriting of the last. Human scale offers its own metaphor. Stand by a river after heavy rain and watch the surface clear water hides the undertow of merged currents. You see only the top, smooth and reflective, but beneath it, two flows wrestle for dominance. That is our galaxy's state, serene to the naked eye, roiling beneath. We live within that mixed water, the product of collision and blending. It humbles the notion of stability. Even our cradle is in motion, slowly evolving through ancient tides. The breakthrough arrives in the coldest signal hydrogen's 21-centimeter line, a radio whisper that traces gas invisible to optical eyes. By mapping that frequency, astronomers see where fresh hydrogen still streams into the Milky Way, feeding the spiral arms like veins feeding a heart. These are the arteries of creation. They replenish the reservoirs that will one day collapse into new stars and perhaps new planetary systems. The idea that galaxies are self-sustaining through such cosmic infall changes how we imagine time. Creation is not a moment, it is a rhythm. We can almost hear it. The static between stations on a radio, the background hiss of hydrogen across space, is a hymn to continuity. It says the galaxy still breathes, while stars burn and die. The inflowing gas ensures the next generation. Without that slow rainfall of matter, the spiral arms would fade, and our night sky would thin into darkness. In every hydrogen map lies a quiet promise. This is not the end, only a pulse in a long cycle. Why? It matters lines surface naturally. First, because this process explains our origin not as accident but inheritance. Second, because it shows that galaxies are not static backdrops, but living ecosystems. Third, because it reminds us that destruction and creation are entwined, not opposites. The death of one galaxy becomes the childhood of another. But the story is not without unease. The stream that once fed us continues to orbit, still unraveling. In time, even the remnants of Sagittarius will scatter so thinly that no trace remains. The Milky Way will look smoother, more perfect, and in that perfection will lie forgetfulness. The scars that made us will fade from view. What else might we overlook simply because it hides too well in beauty? The micro-questions return like footsteps. How much of what we call our galaxy truly belongs to us? How many of our atoms came from other skies? What happens when the next collision comes? When Andromeda approaches and the current begins again, will future observers trace our stars as another broken stream in some larger spiral? Perhaps the universe writes continuity not in permanence but in rhythm. Stars rise, fade, and feed the next. Streams form, dissolve, and feed the next. Civilizations, born of starlight, may pass their signals onward before they vanish. We are all tributaries in motion, merging into a sea we can barely map. So the grain of sky from the previous chapter, once thought empty, connects to this river of motion. The worlds we found there orbit suns forged from the debris of ancient mergers. The light we measure carries the memory of that union. To follow the thread of origin, we must travel deeper toward the center, where gravity shapes not just rivers of stars, but the very fabric of time itself. Begin with a clear view. In the crowded star fields toward our galaxy's heart, a handful of bright points trace tight ellipses over years. Each returns to almost where it started. Late, but precise, as if answering to a metronome hidden behind darkness. Telescopes record their positions night after night, building long strings of dots that curve, kink, and close. The curves are clocks. The kinks are gravity's handwriting. No luminous object sits at the focus, yet the math insists there is mass there, heavy beyond imagining, compact beyond comparison. This is the clue. One star, the fastest of the set, dives inward and slings back out, completing a loop in roughly a human decade and a half. Its speed surges near closest approach, a sprint so quick that only a deep potential well could cause it. The orbit's precession, a slow turning of the ellipse, matches the corrections expected when space and time themselves act as participants. Not stage. We cannot photograph the culprit directly. We do not need to. The orbits accuse it with every lap. Contradiction tests the claim. What if a swarm of dark remnants, many small masses together, mimics a single giant? In that case, the orbit would wobble irregularly, perturbed by nearby clumps. It does not. What if some new theory of gravity could stand in for an unseen object? Modifying force laws on these scales, competing models have been proposed, yet the clean closure and the relativistic redshift during the star's sprint point to a compact source that curves spacetime as expected. Could anything else compress 4 million suns without emitting steady light? Stand at the lip of a waterfall and you will feel the metaphor. far from the drop. The river seems mild. Near the edge, the current accelerates. Sound deepens. Every leaf glides faster than your eyes can track. That is the inner parsec. The stars are leaves. The central mass is the drop. And orbits are the only safe measurement we can make. If a star drifts too close, tides stretch it into strands. Matter near the edge heats, brightens, and disappears from view. The river continues. But what fell does not return. The breakthrough is twofold. First, precise timing of the sprinting star shows its light stretched on the way out, arriving redder by exactly the amount predicted when time runs slow in a deep well. Second, the ellipse does not repeat in place. It rotates a little each cycle, a relativistic precession that pure Newtonian gravity would not produce. These are not metaphors. They are tests. The center behaves like a black hole, not like a cluster or a trick of force. The result closes decades of speculation with measurements anyone can audit. Now the chase. Instruments improve. Infrared interferometers sharpen the star trails. Radio arrays trace light bent near the brink, composing a shadow against a background of emission. Teams compare models to motions and hunt for small deviations that could hint at extra effects, frame dragging, or a faint disk's push. Each additional year stretches the string of dots into an arc long enough to exclude more alternatives. Could a passing cloud have nudged a star and faked the redshift? The numbers say no. Could unseen companions tug the orbit into deceit? Limits tighten, possibilities shrink. In everyday language, a few stars are moving so fast around nothing that only a deep, compact gravity well can explain it. And the way their light and orbits behave matches the rules that govern clocks and space near such a well. We are reading the cliff by timing the leaves. Why it matters. First, is that we finally weigh the engine at our galaxy's center with a method that does not rely on guesswork. Second, the same tests let us probe whether gravity's modern theory holds in extreme conditions. Turning the sky into a laboratory, no experiment on Earth can match. Third, the center's mood influences the whole city of the Milky Way, stirring gas, seeding flares, and shaping the immediate environment through winds and jets when it feeds. Fourth, these measurements teach a discipline we use elsewhere. Trust motion, then build meaning. Micro-questions keep pressure on the claim. How close can a stable orbit survive before tides tear it? Does the precession angle exactly mirror the theory? Or do we find a small drift that demands new physics? If a cloud falls inward and lights up the region, will the star clocks betray the disturbance? Do we see subtle nods in the orbits that reveal an unseen disk tilting the plane? Human scale helps. Imagine standing on a subway platform as a train storms past. The roar bends time. Your watch does not change, but your attention does. You feel the air pulled forward. You sense power that careens beyond your ability to stop it. The galactic center is such a platform. We cannot board the train or halt it. We can count the cars. We can time its return. We can test whether the schedule drifts. The reveal and new horizon arrive together. A compact object of millions of solar masses sits where no object sits, curving space-time so tightly that orbits become experiments. We verify redshift. We confirm precession. We trace a shadow in radio light. That triangulation turns a tail into a map. From here, we can search for subtler effects. The slow drag of space-time as the central mass spins. The faint influence of smaller bodies in the inner cluster. Even the occasional star torn beyond recovery. The waterfall lip is charted. We know where it is safe to stand. And we know where the rush begins. To learn how edges behave from a safer distance, we follow the winds near a star and the oldest light that still lingers. Begin with heat you cannot see. A probe skims the ragged edge of a star's atmosphere and reads the wind. It finds magnetic switchbacks, shock fronts, and waves that steepen into gusts. A weather system that never rests. The corona is hotter than the surface below. An inversion that resists common sense. Particles accelerate, fields twist, and the breath of the star flows outward until it rakes the orbits of distant worlds. We do not photograph the mechanism. We measure it. Pressure, charge, frequency, the physics of pulses. Clue, then context. The same wind that sculpts comet tails and stirs auroras sets the boundary conditions for habitability. A planet lives inside a furnace's draft. Too much wind and atmospheres erode. Too little and radiation seeps in unchallenged. Why does a star pour out so much energy where it should be thinnest? Why do waves born in tangled magnetism lift heat like invisible elevators? Why should weather at a star's skin matter to beings sitting far away in the cold? It matters because climate begins in the star, and climate frames every story a planet can tell. Think of it like this. The star is a tide machine, and space is the bay it moves. Instruments close to the surf sample foam and spray, while farther sensors track swells that cross the gulf for days. From these notes, we build a score. The rhythm explains radio blackouts, satellite drag, and electrical storms on worlds with metal in their bones. It also explains why some young planets keep their air and others bear rock to the void. The small, local wind is a universal gatekeeper. Now widen your attention until the sky looks grainy and quiet. There is a light older than stars themselves, a microwave glow that saturates every direction. It is not a picture with shapes. It is a temperature field mapped to astonishing precision, modeled by differences a few parts in 100,000. Those tiny wrinkles are fossil acoustics, pressure waves frozen into the earliest plasma as the universe cooled enough to allow light to travel freely. The pattern is a ledger of initial conditions. Density here, density there, a recipe that baked galaxies into being. Contradictions test the ledger. If the early universe were perfectly smooth, nothing would clump and stars would not ignite. If it were too lumpy, gravity would have locked matter into blackness and denied the long era of stars. Instead, we find the Goldilocks texture, a compromise that seeds structure without smothering it. Do our models of matter and expansion fit this map without contortion? Do later measurements of galaxy clustering rhyme with the first light speckle cross-checks Titan? The sky's oldest whisper agrees with the census of what came after. Breakthroughs hide in how different scales talk to each other. The probe at the star and the map of the first light both describe transport. In one case, energy climbs through knots of magnetism and escapes as wind. In the other, the first light carries the memory of sound waves that once rang through a hot fog. Energy moves, patterns persist, and memory becomes structure. If the universe had written a single lesson, it would be that motion under steady rules builds complexity from simple starts. The chase picks up across instruments and epochs. We compare the star's wind to the patterns of young stars in clusters where birth is fresh. We test whether bursts of wind correlate with changes in planetary atmospheres years later. We match the first light map to the distribution of voids and filaments today, testing whether gravity's bookkeeping kept faith over billions of years. Micro-questions keep the pressure on the claims. How does a star's spin rate tune its wind? And how does that tune a planet's chance at calm seas and long seasons? Do subtle alignments in the first light map hint at physics beyond our neat models? Or are they the dust of measurement and chance? If the fabric at the beginning was a little different, would galaxies have formed in time to host long-lived suns? Why it matters. First is existential. The wind from a star sets the ceiling and floor of a planet's habitability. Second, it is methodological. The first light map verifies a whole framework of cosmology by giving us a target precise enough to fail. Third, it is temporal. By bracketing the present between a star's near breath and the universe's first image, we learn whether we inhabit a stable window or a brief clearing in fog. Fourth, it is ethical in a quiet way. Decisions made on one blue world should be sized to the span of the candle we burn and the night we inhabit. The reveal sharpened through decades arrives with a calm severity. The age of starlight is finite and short compared with the universe's full life. A brief local holiday in an otherwise lengthening night. Support evidence-led films. Like and subscribe to the Quiet Universe channel. What follows from this is not despair, but orientation. Stars will thin. Red dwarfs, careful spenders, will burn longest, painting a late cosmos with dim embers. After them, matter cools, collisions slow, and the stage goes dark by degrees. Museum lights dim room by room. We stand now in a gallery still bright enough to read. The exhibits around us are wind, drift, and the baby picture of everything. They tell us we arrived during an age when measurement is possible. The signals are still above noise. The clocks still keep time. Human scale steadies the thought. Picture a cinema after the credits. House lights rise just enough to guide you out. You turn and see the screen faintly gray, the projector cooling. That gray is our microwave background. The rising light is the starlight epoch still on. We sit in the aisle with a notebook, trying to capture what we learned before the ushers sweep the floor. It is not tragic that the showing ends. It is meaningful that we were present for it. Simply put, we live in the crossfade between two kinds of light, the late wind of nearby stars and the first light stretched thin. Between them, we test ideas, verify equations, and decide how to use our small window well. The right response to a short era is not panic, but precision. Measure well. Compare honestly. Preserve signal. Pass on instruments more faithful than memory. If edges teach anything, it is that endings are gradients, not cliffs. The last night is not a switch, but a long dimming. That knowledge frees us to act without melodrama and to ask better questions. What will we choose to map while mapping is still clean? Which faint signals will we train the next watchers to pull from noise? The philosophical echo now waits, where evidence becomes meaning and maps become mirrors. What we have traced across these acts is not just astronomy, but a mirror for how we learn. Each experiment began with restraint. Each revelation came from listening to the smallest change. We learned that worlds reveal themselves by a dip in brightness, that galaxies grow by digesting their kin, that time itself curves near invisible thresholds, and that the oldest light still hums beneath our noise. Knowledge, it seems, prefers the margins. When we step back, the picture is not chaos but continuity. A planet's shadow, a stream's drift, a star's orbit, a background glow, each is a rhythm of cause and inheritance. The same rules that shape orbits govern the swirl of weather on our own sky. Gravity and heat, pressure and resonance. These are not cosmic luxuries. They are household laws scaled beyond our comfort. The universe does not shout its secrets. It whispers them through patterns that only patience can hear. Perhaps this is why observation often feels like devotion. To measure faithfully is an act of humility. The instruments that stare without blinking become extensions of that patience. Kepler counted the faintest dips. Gaia tracked the faintest motions. Planck mapped the faintest heat. Together they proved that silence, when recorded long enough, speaks. Their discipline rewrites an old idea. The sacred is not in miracles. It is in measurement. At its core, this philosophy bends light into ethics. To witness without rushing, to test without presumption, to doubt without surrendering meaning. These are the principles of both science and awareness. The stars are not symbols, yet they train us in symbol making. They remind us that significance emerges not from rarity, but from repetition. A billion orbits, a million mergers, all guided by the same invisible tension. There is order here, but not the kind that comforts. It is order through change. Think of a darkroom again. That single red bulb, that patient watcher waiting for the image to appear. What develops on the paper is never exactly what we imagined, yet it always rewards those who wait. The cosmos functions the same way. It does not reveal itself to haste, only to rhythm. Each generation of observers adds a little contrast, a little focus, until something like meaning surfaces. Then, inevitably, the exposure continues, and meaning shifts again. The pattern we inhabit is brief. The age of stars will pass. Their light will thin, and matter will drift toward a quiet equilibrium. Yet the fact that we can conceive of this future gives it grace. Awareness, temporary though it is, transforms the indifferent universe into a story. We are not the climax. We are the moment of comprehension within an ongoing process. The galaxy eats, radiates, collapses, but in one small interval it looks back on itself through us. What this means is that we belong not because we control, but because we notice. Our intelligence is not a rebellion against entropy. It is entropy thinking. Every measurement we take is a confession that the cosmos has already written us into its script. The goal was never to master the stars, only to understand the inheritance that made us possible. To put it another way, we are the universe's sense of recall, a mind made of stardust asking what stardust remembers. We measure light because we, too, are patterns of light slowed down into matter. The very tools we build mirrors, detectors, equations are reflections of the structure we study. The border between observer and observed is thin as a photon's path. One paraphrased truth lingers: we learn to weigh the dark by the light it steals. Each shadow, from a planet's crossing to a black hole's mouth, is an opportunity to infer what cannot be touched. In learning to read those shadows, we have learned to read ourselves. Now the gallery darkens. The museum lights that were stars begin their long fade, and the last image on the cosmic film is still developing. But in that closing dimness, there is serenity. The fact that we are here to witness it at all is miracle enough. We are surrounded by ends that create beginnings, by silences that store information, by distances that unite us through their very scale. So when the final photon of starlight passes, it will not vanish in vain. It will have carried the record of everything that ever shone, every measurement ever made, every life that wondered why. That is the legacy of the bright era. The sum of curiosity turned luminous. What remains is the question that will outlive every observer when the last light fades and only memory endures. Will the universe still remember that it once looked back?